Okay, we're going to be looking at problem number 5 of practice test 3. This is a uniform rod of length 2 meters with a mass of 0.2 kilogram, pivoted to rotate without friction about a horizontal axis that is perpendicular to the rod, and passes through the rod at a point 0.5 meter from one end. The rod is held in a horizontal position and released. We're asked to find A, what is the initial angular acceleration of the rod just after it's released, and B, what is the angular velocity of the rod as it swings through the vertical. We show here a diagram of the rod on its pivot. And what we want to do is model the rod, each section, the left section and the right section, by the center of gravity located, or the mass at the center of gravity for each section. And we're going to do this for the purposes of calculating torque and later on for the purposes of calculating the change in gravitational potential energy. So I show the location of the center of mass and give it mass 1. It's located at distance r1 from the point of rotation. And for the right side of the rod, mass 2, indicating the center of mass for the right side of the rod, located at distance r2. Now, what is Newton's second law in rotational form? Well, we know that that's the net torque is equal to the moment of inertia times the angular acceleration. And how many torques act on the rod? Well, there are two torques. One is the torque from gravity acting on the left side of the rod, and the other is the torque from the force of gravity acting on the right side of the rod. And we can denote those as torque 1 equal to the mass 1 times gravity times the distance from the point of rotation r1, and torque 2 equal to negative mass 2 times gravity times r2, the distance of the center of gravity from the point of rotation. And we will denote counterclockwise as positive, clockwise as negative. What is the moment of inertia? Well, for the rod rotating around its center, we know what the moment of inertia. We can get that from a tabulated value. And then we can use our parallel axis theorem to find the moment of inertia if it's displaced from the center of mass. And we show here such a calculation where I, the moment of inertia, is equal to the moment of inertia times at the center of mass plus the mass times the displacement squared. And that's equal to 1/12 ml squared plus m times 1/8 L squared. And that comes from the parallel axis theorem. Now let's write down the specific equation, putting in everything we've just talked about. And so we'll have m1gr1, which is torque 1, minus m2gr2, which is torque 2, is equal to the moment of inertia times the angular acceleration. And let's list all our values. M1, which is 1/4 the rod, is equal to 0.065 kilograms, 1/4 the total mass. M2, which is 3/4 the length of the rod, and that's equal to 0.195 kilogram. R1 is 0.25, R2 is 0.75. Notice that's halfway along the left side, halfway along the right side. Now let's calculate the moment of inertia. And of course, the moment of inertia is, after plugging in the numbers, 0.103 kilogram meter squared. Now what is the total torque? And I show here a calculation of the total torque. And we just sum the torque from each component, M1G R1 minus M2G R2, and we come out with minus 1.274 Newton meters. Now let's solve for the angular acceleration, because now what we have is we have this value and we have this value. So now all we have to do is get the angular acceleration. And we have minus 1.274 equal to 0.13 times angular acceleration gives us an angular acceleration of minus 12.37 radians per second squared. Now, can we use conservation of energy for part B? We have that the change in potential energy plus the change in kinetic energy equals 0. And that would be the change in gravitational potential energy of the first part, the left side, plus the change in gravitational potential energy of the right side, plus the change in rotational kinetic energy is equal to 0. Now we can already see that when this rotates and swings down, the change in gravitational potential energy of the left side is going to be a positive. That will increase, and the change in gravitational potential energy on the right side will decrease. Once again, we're modeling as a point mass located at the center of each section, and so the rise in potential energy for mass 1 is just mg m1g r1, and for mass 2 will be a minus m2g r2. And we can calculate that. And I set the equation up. Our goal is to find this omega squared here. And let's solve for it. And solving for it, we have that omega squared is equal to this quantity, which is the quantity of the first two terms on the left-hand side of the equation divided by 0.103, all quantity multiplied by 2. And we come out with the angular velocity equal to 4.97 radians per second, and in the clockwise direction. End of module.